In the previous video, we introduced the concept of polyatomic ions. Today, we're going to be looking at a topic that is frequently overlooked, but contains what is maybe some of the most practically useful knowledge in general chemistry. The topic of this video is chemical nomenclature. Let's review a few things first. An ion, if we remember from last time, is essentially an atom with an overall charge. An ionic bond is a bond that forms between ions, or atoms that have vastly different electronegativities. A covalent bond forms between atoms with more similar electronegativities. Last but not least, a polyatomic ion is a covalent molecule that has an overall charge and forms bonds like an ion. We've spent quite some time discussing ionic and covalent compounds, but it might have been noticed that we haven't yet put forward a system for naming them. For example, why is sodium chloride called sodium chloride? Why is lithium nitrate called lithium nitrate? Those are the questions we're trying to answer today. We know that part of naming molecules comes from looking at the atoms that comprise them, but the reality is a bit more complicated than that. And the point of this video is to introduce a simple system with which we can take a single look at a chemical's name and immediately know its chemical formula, or vice versa. Again, knowing the patterns behind nomenclature is extremely useful on a practical level. There are two reasons for this. Firstly, any chemist in a professional setting will probably be expected to know the names of the chemicals they're working with. A chemist who has to look up the names of each and every chemical in their beakers will be a very inefficient worker. Secondly, the reality is that it is effectively impossible to memorize the names of all the chemicals in the world. It's possible to memorize the names of all the elements on the periodic table or something along those lines, but there are so many combinations of atoms out there that it's not feasible to commit all their names and all their formulas to memory. By introducing a system, we can simply use patterns in nomenclature to predict names and formulas with a minimal amount of rote memorization. With that in mind, let's get started. We're going to be looking at the naming rules for ionic compounds first. There are three cases that are possible here. Our first and simplest case involves compounds comprised of a metal and a nonmetal. Naming such compounds is pretty simple. All we have to do is write the name of the cation, which is usually the metal, followed by the anion, which is usually a nonmetal. The only change we need to make is adding the suffix "ide" to the end of the nonmetal's name. Here are two examples: sodium chloride and lithium iodide. Chlorine becomes chloride, iodine becomes iodide. That's it. Case 2 involves compounds made up of a monoatomic ion bonded to a polyatomic ion. If the bond is between a metal or cation and a pi, the metal's name goes first. If the bond is between a nonmetal or anion and a pi, the name of the pi goes first, followed by the nonmetal with the suffix "ide." Our first example is sodium bicarbonate. Sodium is a metal and bicarbonate is a pi, so we write them with sodium first and the polyatomic ion second. Our second example, by contrast, is ammonium chloride. Chlorine is a nonmetal, so it gets written second with the suffix "ide," becoming chloride. Ammonium, the polyatomic ion, goes first, giving us ammonium chloride. Just remember this simple rule. If there's a metal involved, the metal goes first. Case 3 is a bit unique. It involves ionic compounds that have water in their lattice structure. This usually happens when an ionic compound existing in a powder form absorbs moisture from the air, and the water molecules attach themselves to the cation. When this happens, the resulting substance is called a hydrate. It's important not to get hydrates mixed up with dissolving a salt or powder in water. A hydrate compound still maintains its lattice or crystalline structure. It's not involved in a solution or something of that nature. When we look at a hydrate in a laboratory, it still appears as a powder, not as a liquid. To name a hydrate, we combine the name of the regular or dry compound with a term that denotes the number of water molecules bonded to the cations. A compound that is not a hydrate and does not have water in its lattice structure is called an anhydrous compound. The formula for hydrates, by the way, involves the formula of the compound followed by a dot. This dot isn't exactly a period. If you remember learning multiplication, you might remember a teacher saying that it's not always a good idea to use the standard multiplication symbol since it's easy to get it confused with the variable x, since both of them look like a lowercase letter x. Instead, the teacher may have recommended using a dot to represent multiplication. The same symbol is being used here. The dot is followed by the term NH2O, where the variable n is changed to the number of water molecules bonded to the cations. For example, here we have beryllium sulfate tetrahydrate, which has this chemical formula. From this, we see that there are 4 water molecules bonded to the beryllium cations. Our second example is sodium carbonate decahydrate, which has a grand 10 water molecules bonded to the sodium cations. Now we might notice the prefixes tetra and deca written before the word hydrate in each of these examples and wonder where these come from. Down here, we have a table of hydrate prefixes based on how many water molecules are present. Start copying these down if you'd like to. I'll scroll down in just a minute. The prefixes themselves are underlined in green. That's the rest of them. By the way, the prefixes are the important thing to remember from this table. Last case now. In case 4, we have compounds that involved a transition metal bonded to a nonmetal or a polyatomic ion. A transition metal, if we recall, is a metal found in the D block of the periodic table, in groups 3 through 12. These metals are unique in that they can form cations with different charges depending on the way they're bonded. For instance, iron can either have a positive 2 charge or a positive 3 charge. It can transition between these 2 charges if it helps to think of it that way. To name these compounds, we write the name of the transition metal, add the Roman numeral of the charge attached to it, then write the nonmetal ending with the suffix "-ide". It goes without saying that knowing which Roman numeral to write requires us to understand the bond that forms between the atoms involved. If a polyatomic ion is involved, we still need to write the Roman numeral, but we don't need to change the suffix to "-ide". For example, here we have a compound involving iron and chlorine. Chlorine has 7 valence electrons and forms anions with a charge of -1. This means that iron 2 chloride, as written here, requires there to be 2 chlorine atoms, since iron has a charge of +2 as denoted by the Roman numeral. It's quite a common mistake to assume that the Roman numeral is indicating how many chlorine atoms there are, but this would be incorrect. The Roman numeral is there to tell us what the charge number on iron is. Our second example is mercury 1 oxide. The charge on mercury is +1, whereas oxygen always makes anions with a charge of -2. In order for these charges to cancel one another out, there needs to be 2 mercury atoms, so we end up with the formula Hg2O. For example problems. Example 1 would like us to write the chemical name of CuCl. Cu is the element symbol of copper, and Cl is the element symbol for chlorine. Copper is a transition metal, chlorine is a nonmetal. This is an example of case 4. All we have to do is write the metal first with its Roman numeral and change the nonmetal suffix to "-ide". But how can we find out the correct Roman numeral? We have to look at the formula. Chlorine forms anions with a charge of -1, and there's only 1 atom of copper to go with it. That means that in order for the charges of these 2 atoms to cancel each other out, the charge on copper has to be +1. The Roman numeral is 1, or I. Our final answer is copper 1 chloride. Example 2. Write the chemical name of Fe2SO43. This compound involves iron, so this is case 4 showing its face again. In this instance, SO4 is the sulfate polyatomic ion, so we know our final answer is going to be iron blank sulfate. The Roman numeral is what goes in the blank. To find this elusive Roman numeral, we need to know what charge on iron can balance out the charge on the sulfate Pi. The sulfate Pi normally has a charge of -2, but the subscript 3 outside the parentheses tells us that there are in fact 3 sulfate ions involved here. So we do -2 multiplied by 3 to get -6. Now we have 2 iron atoms to work with. Iron can either have a +2 charge or a +3 charge, but to get 2 iron atoms to have a combined charge of +6, we need the charge on each individual iron atom to be +3. The Roman numeral is therefore 3, or III, and the final answer is iron 3 sulfate. As a quick aside, some of the older literature might refer to iron 3 sulfate as ferric sulfate. This name comes from an older set of nomenclature rules and isn't recommended anymore. But for anyone who's interested in flipping through older books and journals, it's important to recognize the changes in nomenclature that have happened over time. Alright, back to this. Example 3 says, write the chemical formula of aluminum phosphate. So, this time, we have the name of the compound, and we're trying to use this information to find the corresponding formula. Let's see what we can do here. Our first step is determining which case this problem belongs to. Aluminum is a metal, but not a transition metal, and phosphate is a polyatomic ion. So this is an example of case 2. All we have to remember is to write the metal symbol first and make sure the charges cancel out. Phosphate has a formula of PO4 and a charge of -3. So let's try writing Al PO4 and go from there. There we are. Now, aluminum forms a cation with a charge of +3. Would you look at that? Our charges cancel without us having to do anything else. This is our final answer. One final example. Example 4 would like us to write the chemical formula of cobalt-2 chloride hexahydrate. Don't panic at the sight of this monstrosity. All it is a combination of cases 3 and 4. We have an ionic compound involving a transition metal that just so happens to be a hydrate. Let's take this one half at a time. We'll first figure out the formula of cobalt-2 chloride and leave the hydrate part for later. The Roman numeral tells us that this cobalt atom has become a cation with a charge of +2, and we're now so well acquainted with chlorine that we know it has a charge of -1. This means there must be 2 chlorine atoms for the molecule to have an overall charge of 0. The chemical formula of cobalt-2 chloride must be CoCl2. Now to tackle the hydrate. The problem gives us the term hexahydrate. And if we look back at our table, we'll see that the prefix hexa denotes the presence of 6 water atoms. The final answer becomes COCl2 dot 6H2O. Written like so. Not too bad, I hope. This video is going a bit longer than I thought, and we are at the end of one section, so to speak. So feel free to pause the video and take a moment to stretch before we continue. Now that we've talked about naming ionic compounds, we of course have to talk about naming covalent compounds. Fortunately for us, there are only 3 cases of covalent compounds instead of 4. Let's begin with case 1, which are compounds composed of 2 nonmetals. The hardest part of naming such compounds is figuring out which one is named first. To determine this, we have to turn to our periodic tables. The nonmetal with more metallic character goes first, and the nonmetal with less metallic character goes second. Metallic character increases as we travel from top to bottom and from right to left of the periodic table. So elements closer to the bottom left of the periodic table will have more metallic character. The nonmetal with less metallic character comes second and ends with the suffix "-ide, which is a bit of a common theme here. After determining the order of the atoms, we have to add prefixes to denote how many of each atom is present. These prefixes are listed in our table of hydrates up here. Oh, a quick reminder here. If there is only one atom of the first atom, the atom with more metallic character, we don't have to add the mono prefix. We can just write it as is the case with our first example, boron trichloride. We don't need to write monoboron trichloride. Our second example is dinitrogen tetroxide, which has 2 nitrogen atoms and 4 oxygen atoms. Convenient, isn't it? We can tell the exact number of atoms in this molecule just by looking at the name. That's the magic behind nomenclature. Case 2 involves a compound composed of hydrogen and another nonmetal dissolved in water. This is another special case. When some compounds with this composition are dissolved in water, they form substances called binary acids. We haven't discussed acids in any sense as of yet, but it seems better to introduce naming rules for them now than to have to talk about nomenclature again later when we arrive at acids and bases. To name binary acids, we begin with the prefix hydro, a prefix that tells us hydrogen is present. Attached to this prefix is the name of the other nonmetal ending with the suffix -ic. After this comes the space, and after the space comes the word acid. Here are 2 examples. When the compound hydrogen chloride, or HCl, is dissolved in water, it becomes hydrochloric acid. The AQ in parentheses tells us that this is an aqueous solution, a substance that involves water. Remember, this is not the same as a hydrate. A hydrate still looks like a powder or a solid, whereas an acid is very clearly a liquid. The second example is when dihydrogen sulfide is dissolved in water, where it becomes hydrosulfuric acid. Notice that the prefix di on dihydrogen is dropped when we add the prefix hydro. Case 3 involves compounds that combine hydrogen with a polyatomic ion that includes oxygen. These compounds are called oxoacids, and they are the second group of acids we're discussing today. They contain hydrogen, oxygen, and one other element. Oxygen and the other element are usually part of a pi. To name these acids, we first write the name of the pi, but we have to change its suffix. If the pi ends with ate, we change it to end with ik. If the pi ends with ite, we change it to end with us. Then we add a space. After the space, we write the word acid. Once again, two examples. First, we have sulfuric acid, which combines hydrogen with the sulfate polyatomic ion. Our second example is chlorous acid, which combines hydrogen with the chlorite ion. Four more examples now, this time for covalent compounds. Example 5 says, write the chemical name of S3F6. This is a prime example of case 1, since both sulfur and fluorine are nonmetals. There are 3 sulfur atoms, so it takes the prefix tri and becomes trisulfur. There are 6 fluorine atoms, so it gets the prefix hexa and becomes hexafluoride. We know sulfur is written first, since it is to the left of fluorine on the periodic table and therefore has more metallic character than fluorine. Our final answer is trisulfur hexafluoride. Example 6 would like us to write the chemical name of H3PO4. PO4 is the chemical formula of the phosphate polyatomic ion, which contains oxygen, and hydrogen is involved in the compound, so this is case 3. We're looking at an oxo acid here. Phosphate gets the suffix ic and becomes phosphoric. And then we add a space, and then the word acid. Phosphoric acid. Phosphoric acid, by the way, is a major industrial chemical, and it's used to make fertilizers, detergents, and all sorts of things. Example 7 says, write the chemical formula of nitric acid. Since the prefix hydro is not present, nitric acid belongs to case 3 rather than case 2. It's another oxo acid. If we disregard the ic suffix, we might notice that nitric acid sounds either like the nitrite or nitrate polyatomic ions. Because the suffix is ic, however, we deduce that the original pi must end with ate, so nitrate it is. The nitrate polyatomic ion has a chemical formula of NO3 and a charge of -1. Hydrogen likes to lose 1 electron, so it has a charge of +1. The formula of nitric acid, then, is HNO3. Alright, this is the last example problem of the whole video. Example 8 would like us to write the chemical formula of disulfur decafluoride. I'm not going to go on at length about this one. Disulfur implies 2 sulfur atoms, and decafluoride indicates 10 fluorine atoms. Sulfur is, again, more metallic than fluorine, so it goes first. The answer is S2F10. That's it for chemical nomenclature, but here are a few concluding remarks. It's important to note that this nomenclature system is established by the International Union of Pure and Applied Chemistry, or IUPAC. An alternative system is provided by the Chemical Abstracts Service, or CAS. The CAS assigns each chemical a number called the CAS registry number, and these numbers are widely used in databases and other places where chemical data is stored. For obvious reasons, the IUPAC system tends to dominate in chemistry classrooms and in everyday conversation between chemists. Trying to remember numbers for every chemical out there is difficult, and common names have a tendency to go in and out of fashion. Sodium chloride has almost always been called salt, so that's not a problem. But sulfuric acid was once called oil of vitriol, a term that's almost never used today. Common names are a useful shorthand, yes, but they aren't always the most scientifically accurate or precise terminology. That's why the IUPAC system enjoys the widespread popularity that it does. It serves as a unifying factor. In the same vein, I have to mention for the sake of some viewers that current IUPAC guidelines don't recommend some of the alternative spellings that are a feature of British or Commonwealth dialects of English. For example, in the United Kingdom and the Commonwealth, many older sources spell sulfuric acid with the letters PH in place of F, but the IUPAC prefers the latter. I'm not quite sure how common the traditional Commonwealth spellings are today, but the IUPAC doesn't recommend them to the best of my knowledge. If anyone is familiar with how this is resolved in countries where the Commonwealth spellings were traditionally used, do let me know in the comments. I'd be very interested to know. In our next video, Unit 2, Video 5, we will introduce the VSEPR theory of molecular geometry. Thank you for watching.